Okay, so in section 7.3, we're going to look at two different types of solids and finding their volumes using calculus. One type of solid we're going to get by taking a shaded region and rotating it around an axis, like around the x-axis or around the y-axis, or maybe around some other axis. And then the other type of solid we're going to get by describing what its cross-sectional areas look like. And that's the first type that we'll look at here. So we have a solid that is described this way. It has its base in the xy plane contained by the parabola x equals y squared and the line x equals 4. And the cross sections are described as isosceles right triangles with one leg in the xy plane. So what we want to do is we want to imagine we take a big lump of clay and just plop it on top of the x and y axis. We're going to mold it as it comes up out of the plate. We're going to mold it so that its cross sections are isosceles right triangles. Okay, so that would look like this coming out of the board. Here's an isosceles right triangle. If I slice this perpendicular to the x-axis, each cross section is going to look like an isosceles right triangle coming out of the plate. It could be like that, or it could be like that. It doesn't really matter. It's going to be the same either way. Okay. So when I slice it right there, that is the leg of one of the isosceles right triangles. Now, to see it coming up out of the plane, we want to draw it in 3 dimensions. And so if you rotate your y-axis and your x-axis slightly so that we get some perspective, the red line that I've already drawn is the same as this red line. And then we can now see the right triangle coming up out of the xy plane with the right angle right there in the corner. So that's an isosceles right triangle. Those two legs are the same. And then if I took another slice out here, for example, closer to x equals 4, that would correspond to that red line, which is another leg of another isosceles right triangle. This time it's going to be a bigger triangle. And so it would be that isosceles right triangle with those two legs the same. Okay, so you see we get all different sizes of isosceles right triangles by drawing in some more cross sections. And then if I get close to the origin, I'm going to get a tiny little isosceles right triangle down here and eventually leading down to a point when we get to the origin. So if you were going to describe this solid, you could say that along the back wall, it's a vertical wall that kind of curves around in the shape of a parabola. But on the front side, looking at it from this direction, there's not really a wall. You can think of it as kind of like a slanted roof that curves toward the origin. And so we've molded our lump of clay to fit that description so that every time we slice it perpendicular to the x-axis, we get a new isosceles right triangle. Okay? So just as we did in two-dimensional problems, we're going to take skinny little slices and add them all together. So if I take one slice of this solid, imagine one isosceles right triangle, and we're going to give it a tiny bit of thickness, just like we did with the rectangular approximation method. We give it a little bit of thickness, and so this thickness, notice that that is parallel to the x-axis, so that is our dx, our infinitesimal thickness dx, just like this paper triangle that I used to demonstrate. It doesn't have much thickness, but if I stacked up 500 of these, I would eventually build out the whole thickness of that solid. Okay? And now our task is to figure out what are the dimensions of this slice. What are the base and the height? So we look back at our 2D drawing. We're really trying to figure out what is the length of this segment. And sometimes it helps to write down the coordinates of the endpoints. If I'm at any general x value, what would the y value be? What would it be? Y is equal to root x, and down here y is equal to negative root x. And so this point would be x comma root x, and this point down here would be x comma negative root x. And so what is the length of that segment? Good, 2 root x. Okay, so now I can replace those question marks with 2 root x and 2 root x. Why are they the same? Because it's isosceles. Okay, and so now we're going to write down the volume of one slice. It's a triangular, 1/2 the base times the height times the thickness. And so in this case, our base is 2 root x, and our height is also 2 root x, and our thickness is dx. And so that is 2x dx when we simplify. That's the volume of one slice. Now remember, the integral is just like a summation. It adds up a bunch of things. So we're going to add up all the possible slices that we could get. And so the volume of our solid is equal to the integral of 2x dx. So that's going to add up all of those volumes, 2x dx, ranging from x equals 0 until the last triangle that we draw, which is at x equals 4. And so that is x squared. Taking the antiderivative of 2x, you get x squared. From 0 to 4 is 16. And we don't have units. If we did have units, it would be whatever those units are cubed. So it's a volume, so we need cubic units. So for this volume, we get 16. Any questions? That's the volume of this entire solid, this entire lump of clay that we shaped to fit that description. Does that make sense? Okay. Any other questions?
Based on x equals 4, that's flat.
Yes, so we would see a flat triangle looking at the end. Looking at this end here, we would see this triangle looking at the end. Okay? Any other questions? Okay, go ahead and read this description. See if you can make both a 2-dimensional and a 3-dimensional drawing of what's going on here, and then work as a group to come up with an expression that you can use to find the volume of each slice, and then an integral to add up all those slices. Go ahead and work together on that now. All right, so let's see how you're doing here. We have our boundary this time is a circle, which the equation of the top half of the circle would be y equals the square root of 16 minus x squared, and the bottom of the circle would be y equals negative square root of 16 minus x squared. And so if we take a slice perpendicular to the x-axis, that segment, that red segment, is going to be the edge of a square. And so looking at that as a 3D view, that red segment is the same as this red segment, and then we'd have a square coming up out of the xy plane like this. And we can draw several of them. Here's another square coming up out of the xy plane. And then back here, another square coming up out of the xy plane. And so if we draw several of those squares coming up out of the xy plane, we get a solid that looks like this. And so that's what it would look like there, and then from that view. Okay? So each slice is like one of these slices of parallel. And that is what the actual solid would look like. The vertical walls here that wrap around in the shape of a circle, but then over the top, it's actually parabolic. You can see a parallel view of that view. And then, so we can kind of see that there's going to be a parabola kind of shape that passes through that edge, and then the same thing on the back side, a little bit harder to see, but we get that solid if we stack up a bunch of those. We can just focus on one slice, so one square slice with a little bit of thickness, and the thickness again is in the x direction, so that dimension is dx. And then the length of this red segment is going to be 2 root 16 minus x squared. So this would be 2 root 16 minus x squared, and the height would also be 2 root 16 minus x squared because it's a square. And so the volume of one slice is equal to base times height times thickness, which you can simplify and just get 4 times 16 minus x squared dx, or 64 minus 4x squared dx. So that's the volume of one slice, which means the volume of our entire solid is just going to be a bunch of those slices added together. And we can let the integral add those up for us from -4 to +4, 64 minus 4x squared dx. Okay, so I got 341.333. Now, that integral would not be that tough to evaluate by hand. You could do this analytically, that means without a calculator. Now, in this section, you're going to be evaluating a lot of these integrals. Some of them are going to be easy, some of them are going to be hard. So you just kind of need to create some balance for yourself. Do some of them by hand, and do some of them with your calculator. So we don't want your homework to take 3 hours, but I also don't want you to forget how to evaluate basic integrals. And so try to do 2 or 3 every night by hand, and do the rest of them with a calculator to save time.